So yeah, I opted for quite a provocative title because I wanted to take this opportunity to really think about the manufacturing of materials, metamaterials specifically, and how that fits in to materials engineering, and how perhaps we can start to move towards bringing more materials engineering and materials engineers into the field through the network particularly, and through all the activities that we're doing. So Anya's given me a profile which I don't actually recognize, but I'm sure I wrote at some point, but I will just give you a small bit of background on where I sort of came from, and what I'm going to talk about in this talk, and where it originates. I'm a material scientist or engineer, depending on which hat I put on the day, by background. And because of that, my group focuses on particular materials, and we particularly focus in my group on ceramic materials. Ceramic materials to me are really particularly fascinating materials because they're very awkward, very difficult to use, but there's a lot of times when they're the only option and the only thing that can be used is a ceramic. So it's something that endlessly fascinates me. But I'm not going to spend this talk talking about my research. If you would like to hear about my research, you can go to that bit.ly link that I've shortened, where you can hear me talk for half an hour about what my research group does in this realm of ceramic materials and materials characterization. But in this talk today, I really want to focus on the things I think about when I'm involved in the Metamaterials Network. I've been the lead of the Manufacturing and Scale Up Special Interest Group, and as Anya said, I'll move to being the co-investigator from January. And I think that the manufacturing side of things has been really demonstrated, even in these early months of the network, to be quite important, and really to be some of the larger barriers to how we move on with metamaterials at this point. So as Anya mentioned, and I said to people yesterday, it's been a bit of a reflective exercise thinking, okay, so if we want people to come into this, how did I get into this? And I got into this as a postdoc. There was a large program grant funded by EPSA called The Quest for the Ultimate Electromagnetics by Spatial Transformations. And I worked on that project as a postdoc at Oxford from 2011 to 2013. And then I moved to Warwick. So basically I got the opportunity to make my own group, and who's going to turn that down at that point. But it was a really interesting project. And it wasn't something initially when it was advertised and being talked about that I thought would suit me and that would work for me. I didn't really know anything about metamaterials. I thought it was all about knowing about how electromagnetics worked, and I didn't really feel like that's where I wanted to go. But I actually got pulled aside by one of the postdocs in my group and told, you should apply for this, Claire, it will be really good. So thank you, Susie, for putting me now where I am today, by persuading me to apply for this. And she said, it's all about making materials, and it's all about how you make materials in particular ways, and that's what you're interested in, so you should apply. And it was about that. And what we were mostly thinking about in that project, and the thing that's really sort of captured my imagination since then, is about these things like spatial transformations, where we can basically manipulate the way that an electromagnetic wave interacts with a space by changing the material properties. So the classic sort of diagram shown in this picture is where we have a copper antenna and a microwave source. It's easily detectable because it bounces off the copper antenna. It's easy to see. And we make an invisibility cloak, which is an invisibility cloak for microwaves, where we encase the antenna in a space which has the properties which allow those electromagnetic waves to bend around so that they don't show where that antenna is. And to do that is essentially a materials engineering problem. What do you do to this material to make those waves move in that particular way, to change our Cartesian space, our XY space, into this transformed space where we can bend the wave and control the wave path? And when I started on the Quest project originally, I was quite influenced by reading these papers, which were by Yang Hao's group in Queen Mary, and thinking about what that sort of meant for how we make metamaterials. So this picture on the left is a designed cloak, and you can see here what it's sort of supposed to be. It's like a metal wedge, and you're changing the properties of the material above it so you can hide that metal wedge. And the initial design of this material is a material which has a change in permittivity from 5 to 1, and is more or less continually graded as here. And it's really quite difficult to make. And they went in this paper for a process of downsampling to see what effect making the material more straightforward to manufacture and to make would be. And they ended up with a design which had permittivity between 2 and 1, which is a little bit easier to realize, but with a continual gradient. And so you then downsample again and say, okay, well, we'll make these blocks, we'll make very coarse blocks, and we'll say they just have to have these particular properties between 2 and 1. And then in this later paper, they actually made that. And this is a polyurethane foam. It's the sort of thing that you can literally go and buy in B&Q and use as insulation, heat insulation or noise insulation. And it's a 2-part mixture, and you mix it up and you get your polyurethane foam. And what they've done is mix in a proportion of barium titanate particles into each of these blocks. So they have different values. And these match up to this blocks here. And this actually kind of works, but there are some problems with it. There's definitely some areas where things aren't invisible, and arguably if there's areas where things aren't invisible, then it's not an invisibility cloak. But it does kind of work, but it was quite straightforward. And I think as the sort of materials manufacturing side of this large program grant in Oxford, we were thinking, well, okay, can we do something better? Can we at least make something that's one piece of material or has better properties or a greater range of properties? And so we started to tackle some of those questions and problems. And this is kind of where we got to before, well, within the project, I suppose maybe before I left it, or around the time I left it and moved on, was looking at doing things like this. So this is a disk of dielectric variations. You can probably just about see that this is going up to a higher value. It's going up to 16 in the center. It's still supposed to be a continual variation in properties, but it's actually discrete layers. And I think possibly on here it's not very visible to see what the property variations are, but these are all layers, and they've been made out of mixtures of polymers and again barium titanate particles, and placed into a mold and made into this structure. So it is at least one piece. It's a reasonably large thing. It's about 10 centimeters in diameter, and this was a really nice piece of work Quinn Lee did as part of her PhD. So this is kind of where we were with metamaterials when I was working on that project. And this is where we sort of started with it, with thinking about metamaterial manufacturing. So with that in mind, when I started thinking about what I was going to say in this colloquium, I wanted to think about how we can relate what we know about metamaterials to what we actually already know about materials. And I think it's very important to think about where metamaterials get their properties from, but also where materials get their properties from. And whenever we talk about metamaterials, we try and sort of define them and say, this is what a metamaterial is. And we say it's beyond materials, conventional materials, not good enough. We'll go beyond those material properties. And we use this definition. I think this is the definition that's currently on our website. They're materials which are fabricated structural elements, which give them properties that aren't found in nature. And as Anya and Alistair know, I debate this definition, and I want to have a discussion about what it is and what that really means from a materials perspective. But whatever we end up coming around to talk about, we sort of talk about these structural elements. And I realized that I often use this picture from Pendry's paper in 2004, because it's a really nice illustration. And it basically says a conventional material gets its properties from its atoms, and a metamaterial gets its properties from its meta-atoms or its structural elements. In this case, they've drawn out some split ring resonators. And that's a really simple way to explain things. And it's a really nice way to explain things. The problem I have with it as a materials engineer is that it's just not really quite true, because materials don't just get their properties from their atoms. There's a lot of factors that go into what gives a material a particular property, and that has an impact when we think about metamaterials as well. So for those of you in the audience who did an engineering degree, this is probably quite a familiar drawing. For everyone else, this may well just be like, okay, what's that? This is something called a material selection diagram, or an Ashby plot, depending on whether you want to name it after the person who used a lot of them in the textbook. And this plots out properties of materials against each other. And it's designed as a tool to allow engineers to choose the right material for the application. Most of them are mechanically inclined because of where they sort of came from. But so this one is fracture strength, so the strength when the material actually breaks, against the density. And what you see here is large regions for different large categories of materials. So we have foams, we have ceramics, metals, and smaller bubbles that sort of represent certain types of materials in there. And you can see there's some specifically named materials, there's some which are more classes, like wood is in here. And what you generally see and what you generally take from this picture is an idea that if you want a high fracture strength, you have to accept a high density, because everything's going from the lower left up to the upper right. And this is kind of where we feel like we get our properties from. But you'll notice that the regions where you have the properties of the materials are quite large. And that's because we actually do have more control over material properties than is thought if you just think about the atoms. So where do material properties come from? Well, they do come from what atoms are in the material. There's no getting away from that. It does affect what it has. It's not the only factor. So the second important factor, which that the atoms affect the properties of materials, is the way those materials are actually bonded together. And this gives rise to a lot of the material properties in terms of mechanical properties, the stiffness of the bonds and the nature of the bonds. So we classically divide up our materials into different categories, and we divide our bonding into different categories as well. So we have covalent bonding, ionic bonding, metallic bonding, and van der Waals bonding. And you can see in this diagram, taken out of a materials engineering textbook, shows you roughly where these classes of materials sit. So metallic materials tend to sit in this corner where they're mostly metallic bonding. Semiconductors tend to be very strongly covalent. Ceramics and glasses actually sit between and have a mixed ionic covalent character, something that's not always like acknowledged when we talk about their mechanical properties. And polymers tend to be a sort of mixture of covalent and van der Waals, depending on which interaction you're looking at within the structure. And the difference that the bonding makes to the materials is to do with how strongly attracted to each other those atoms are. So it's not just which atom they are, it's also how they're attached to each other. So if you have a material which has a strongly covalent or ionic nature, the bonding is particularly strong, and that gives rise in ceramics to the classic brittle fracture behavior that we see in basically all ceramic materials. And it's fundamental to the nature of those materials, because when you put those elements together, those are the kind of bonds that they form. When we put metallic materials together, the electrons dissociate and we do not have that sort of strong bonding, and that equally has an effect on the mechanical properties. It has an effect where you can actually deform the material quite considerably without fracturing it, and that's really directly where that nature comes from. So if you talk to, say, a materials chemist, this is where they tend to sit. They think about bonding, they think about atoms, they think about the composition of the material. The second place where the origin of material properties comes through is the level that I always think of as being the material scientist's level. Microstructure. Microstructure is incredibly important. And actually, I think that it's a place where we have probably the most control over the material properties, the end material properties, if we're confined to a given chemistry or a class of chemistry. Because we can actually really radically affect the properties of a material by changing its microstructure. And I've pulled out 3 examples here to show you in different ways. So the first one on the left, this is aluminium oxide. So it's only aluminium and oxygen. It's pretty covalent in nature. And these are both the same material. They look quite radically different when we look at their microstructure. So this is what we can see under the microscope. You can see here that we have a much more pure, much fewer defects piece of aluminium oxide here, and the grain structure is much finer. This is a 5 micron bar, this is a 50 micron bar. So what are these materials? Well, the top one was made from super expensive Japanese super high purity aluminium oxide powder, and made very, very carefully. The bottom one is what happens when you're bored in the lab and decide you want to look at a piece of a broken furnace tube under the microscope, and you polish it up and have a look at it. So this is a piece of furnace tube that was broken, and it shows you the defect structure within it. So the top one is the sort of thing we want to use if we're going to make something that needs ultra high strength. The bottom one is what you get if you have to compromise on how you make something because you want to make it into a tube so you can use it in the furnace. And what's the difference in the microstructure here? Well, in this one, we're seeing porosity both at the corners, which we do occasionally see in the high purity material, but also within the grains themselves. And this is very, very impactful on the mechanical properties of the material. You also see quite a wide range of grain sizes, and that again can lead to more regions where defects can form, and therefore a lower fracture strength in the end. And this is indeed what we see. The top material is extremely difficult to break. The bottom material is relatively easy to break, especially after a little while in use. The second example of where microstructure can affect properties is this one I've taken out of a paper by Zhao on zinc oxide. So zinc oxide, really nice electrical material. And in this case, they've made zinc oxide by a few different methods. It's got an additive in, it's got some bismuth oxide and things in it. But they've basically made 3 materials with different microstructures. So similar, basically the same chemistry, but with different microstructures. And you can see from the SEM images that actually sample A and sample B are relatively similar. Sample C is quite a bit smaller in its microstructure. And when you come to measure the current voltage characteristic of these materials, you see that come through in the structure. So these are the same material. It's all zinc oxide, but they're showing quite different behaviors in terms of their electrical characteristics and properties. And this is where we get that degree of freedom of how we can control the properties of the material. So the final one, and one that's probably a bit more relevant directly to metamaterials, this is some work by my student Abhijit Swangi, who I think is out there in the audience while I talk about his work, which is always fun as a student. This is some work he's been doing in his PhD, and I've kind of anonymized the material a little bit because we haven't published it yet. But what we've seen is that in these perovskite materials measured at in gigahertz frequency range, we can get quite a radical change in their relative permittivity at microwave frequencies by changing the density of the material. So if we have something that's pretty dense, we do get those high properties which are characteristic of these materials, but we can control that by reducing the porosity down. And that gives us an intriguing option for doing some materials engineering, and gives some impetus to thinking about, okay, so how can we actually make this one material which has quite radically different properties along its length? And it starts to become a processing engineering question rather than a which material should we use? Well, you use this material, but you can get different properties out of it depending on how you manipulate it. The third origin of materials properties category is to do with the processing. And this is kind of different to the microstructure because it's sort of reflecting the fact that you don't necessarily have the same degree of choice about how you process the material. And 2 particular examples I wanted to express about how this comes through are to do with texturing and orientation effects that come through in the processing techniques. And the second one is to do with residual stress. That's on the next slide. So first, talking about texture and orientation. So this classically would be texturing if we're talking about polycrystalline materials like ceramics or metals, and we have a preferential crystallographic orientation in the material. And we'd talk more about orientation when we talk about polymers. So if you extrude polymer, and whenever I talk about extrusion, I always say it's like making pasta, or it's like squeezing Play-Doh through the Play-Doh toy. We're basically pushing a material through a little mold and making different shapes. So you can make a tube, you can make a filament for 3D printing. This is how they are often made. You can make sheets and films. And the act of pushing that through, or even having it pulled off by the haul-off rollers, gives a degree of tension in the material as it comes out, and that can make some orientation effects in the polymer chains as you pull it through. And that can affect what we see in practice. The second place where we see texture and orientation is typically in structures like these. So this paper is quite an interesting paper. Actually, it's on detecting preferential orientation in X-ray diffraction. It's a very nice paper if you're looking for a sort of starter guide on that kind of thing. What it basically shows is that depending on the type of particles we're dealing with, if we're depositing thin films, we can get a strong degree of preferential crystallographic texture and that can be detected then by XRD. But I think it's quite interesting to look at these top images and see, well, these are the sort of crystallographic planes being represented within the particle. If we have these spherical particles which are just allowed to fly down and scatter, you get quite a random orientation. Once we start to confine the shapes and make more blocky grains, I mean, here drawn as a square, in practice it would be a sort of blocky cuboid-esque thing, you can start to see that you're going to get some preferential alignment, and the vast majority of these are aligned along the surface. When we go to tubular or wire-like structures and we deposit them, it's even worse, and we always see texture in those kind of materials. And often it's the sort of texture we don't necessarily want. We don't necessarily want them all lying down like this. We probably want them sticking up, and that can be quite challenging to pull off. And generally, if you want to influence that kind of thing and change it from the natural effect, you need to use an external field of some kind to generate some ordering in the structure. The second aspect that I briefly mentioned was about the induction of residual stresses in materials. And this is a particular problem in ceramics. I'm going to talk about it a little bit later on in the talk as well, because it is something that is sort of an active research area in my group. But this is a situation where it's actually useful. Some of you might know about yttria stabilized zirconia. It's a material that was very strong interest developed in the 1990s. And it's a way of making a oxide ceramic tougher by a particularly interesting mechanism that involves residual stress. So zirconia at room temperature in its stable crystallographic form is monoclinic. At high temperatures, it's tetragonal. And what was found was if you add a small amount of yttrium oxide to the zirconium oxide, you can stabilize that tetragonal phase at room temperature. Not everywhere in the material, but in enough of the material that you get a degree of that tetragonal phase in the structure. And what was observed in the 90s, this is not the original paper, this is just a nice diagram to show you what's going on, is that if you then had a crack in that material, so perhaps you put in a deliberate crack with a hardness indenter or something like that, and you allowed that crack to move through, there was a change that happened at that crack tip. And what was happening was the energy released by the cracking causes a transformation of the tetragonal phase to the monoclinic phase. And they're not that different, these crystal structures, but they're different enough that you see a volume expansion, a significant volume expansion at the crack tip. And that difference in crystal volume gives rise to a compressive stress around that crack tip, and that acts to push the crack back together. So compressive stresses are very good in ceramics. If you want them to be mechanically robust, you want to engineer compressive stresses as much as possible if you're going to have residual stress. It acts to close that crack. And what that effectively does in sort of mechanical properties language is it's toughening the material. It's preventing the crack from moving through the material and acting as a toughener. And this is one of the big reasons why zirconia is used in applications it's used in today. So two big applications for yttria stabilized zirconia are dental implants, because it's white ceramic, it's very long lasting, and it's very biocompatible. And the second one is in ceramic knives. And it's a very interesting thing. If you buy a ceramic knife, a lot of people won't buy a ceramic knife because they think they'll break really easily. But actually ceramic knives are great. They don't need sharpening. They're really, really strong. And they're all made out of this yttria stabilized zirconia. So not sponsored, but very good thing to have. So if we come back to thinking then about what are the properties that materials have and how they come to be plotted in these areas on this graph, I think the things I've talked to you about explains why when we look at a given material on one of these plots, what we're really seeing is a region of properties. Okay, so if we take something like silicon carbide here, so this is the bubble for silicon carbide. And it actually spans quite a range of fracture strengths. And that's due to its microstructure, it's due to its processing, it's due to its exact composition and the exact bonding type. And some materials have less of that and some materials have more, but they all sit in a range and they all sit here. So when we think about metamaterials and what metamaterials do for us, what they're actually doing is something really interesting, because you have this added degree of freedom, and that added degree of freedom allows you to say, well, I don't want a material that's really, really high density, but I need it to be this strong. So why can't I have a material here? And so you might go and design a mechanical mesh material which has a low density because you've made it through a structural form where you have lots of spaces within the structure. So it is actually a low density overall. It's a lightweighting material, but you've engineered it in such a way that you actually attain a fracture strength of a material that should be much, much denser. And sometimes this is referred to by materials engineers as filling in the white space on the material selection plots. And that's a really interesting concept, I think, to me. This space is where we want to be. This space is where all the wins are. That space is not a good white space. This is the good white space at the top. And you can kind of see a little bit on this diagram where that starts to come through. If you look at this composites material, composites are materials which in some ways are the closest thing we have to metamaterials, right? Metamaterials are mostly composites, and conventional composites sort of starting along the metamaterial track. But the composites that are sort of named within this field are something called carbon fiber reinforced plastic polymers and glass fiber reinforced polymers. And they sit here and here. And you can see that they're sort of poking out into the white space. If they weren't there, you would say something here is sitting in the white space. So in many ways, metamaterials is just doing more of this and pushing more out into the white space and giving us those properties that we can't achieve. But I think it would be a mistake to not say that metamaterials get their properties from the three origins that I've already talked about. It's just that we're adding on an extra one. So what do these additional properties give us? The structural elements. Now, this is a nice excuse for me to put up my absolute favorite metamaterial. This is a, believe it or not, ceramic material that can deform completely. It's from Julia Greer's group, and they 3D printed this ceramic and it can deform and recover its shape completely, which is just ridiculous if you work on ceramics. They don't do that, so it's very interesting. But this is one way to manufacture them. We have these elements that have been 3D printed, so it's an additive manufacturing method, but you can also make them by subtractive manufacturing methods, formative manufacturing methods. And in some cases, you don't actually get something that looks that different to a conventional material. I think it's important that we bear in mind when we're talking about metamaterials and what they look like and what they are, that there has to be an element of structure in, there has to be an element of artificial control over the placement of the features, over where they're sitting in the structure, and over the fact that we have made them do that. It's not just that it happens to be like that. That's more like a natural conventional composite. So manufacturing metamaterials, what are we trying to make when we manufacture metamaterials? Well, the additive kind of features, I think, are things like a split ring resonator. So these are little pieces of metal. They're very carefully designed. So you're looking at everything, the dimensions, the spacing, the gaps, the materials that you're actually using. You calculate all of that and then you deposit it and you make these very nice structures and assemble them into nice arrays. And that's an additive feature because you're only ever adding, you're not taking away, and it's all sort of made in situ. It tends to be quite a sequential process. So you have your material, then you deposit something else on the top. So there's multi-steps involved when we do this kind of work. Subtractive features are basically things like holes. I mean, you might backfill the holes in with something else afterwards, but if we think of them in terms of being, you take a piece of material and you machine it to be how you want it to be. So this this paper I come back to lots because it's got the good images in. So put your good images in the paper because it really helps me out when I'm trying to describe how we make these things. So this is a piece of silicon. A very nice material, it's very well defined, and they're making it into a cloak. So this is the area we want to cloak. There's a mirror here, and they've calculated with this model that we need to drill little holes all over this area to make the material have the properties that it needs. And then they went ahead and did that with a focused iron beam. They went in and drilled holes and placed them all around here, and it seems to work. I find this very interesting because some of these holes are off position, some of them are merging into each other, and it's very interesting actually to see a real metamaterial like this where there's obviously some problems with it, but it's nonetheless working. But that's an example of one where we're drilling holes with a focused iron beam on a nanometer scale. You could equally think about these being drilled with a drill bit or a larger scale device. It's the same kind of technology and how we work on these things. The third one, and the one where I probably sit most of the time, to be honest, is looking at formative features and making manufacturing techniques which give us ways to make materials in a formative way. So we're making the whole thing as one body. We're making it in a form which is a robust structure which is all attached to each other. And in this case, we're looking at things like doing the grading of dielectric properties, calculating the properties that we need. The thickness can be very important, as well as the actual values of the materials. And you can see here various ones that we have done in the group over the years, and here's Yang's one from before as well, and looking at different ways that we can process these materials together. Okay, so hopefully that's brief foray through the origin of properties has convinced you there are 4 origins of metamaterial properties. It is not all about the structural elements. It's also about the actual material properties as well, the atoms, the microstructure, and the processing route that we take. And I think if we're going to be able to manufacture metamaterials and really push some of these technologies through, we need to be aware of the effects of all of these things and really work on them. But in many ways, it's actually a natural progression from what we work on as materials engineers, as people who make things. These are the sort of things that we're used to dealing with. So the question occurs to me that I don't actually know that many people who are actively working on this. I certainly don't work on it all the time. Most of my group are working on other things, which it's not an easy thing to work on. So we work on other things which are somewhat closer to being easily worked on. So in the second half of the talk, I want to talk a little bit about what some of the problems are with working on manufacturing metamaterials, and perhaps suggest a few ways that we could try and find a more common ground to work on these things together a bit more between the metamaterials community and the manufacturing community. So number 1, and a big problem that we found and that Abhijit has been working on, my PhD student, is we don't always know what the material properties are. And they do vary quite considerably with microstructure when we put them into composites. And it's not as simple as looking up or asking someone, okay, do you have a material with this property? And I have been asked that a few times, like, do you know a material that has this electromagnetic property, a value of this one? And it's a really difficult thing to answer. And a manufacturer might hand you a data sheet, but then you're confined to buying something from them, not to making what you need. But we know from the measurements we've done in the group that you change the porosity of a material and you're going to get quite significant differences. So what that means in practice is if you have to change your process temperature and therefore you affect your ceramic microstructure, you're going to see quite a radical difference in the dielectric properties. We could be talking about going from 20 here to more like 100 in the permittivity of these materials, and that's quite a significant effect. So that's the first one. The second aspect of this is to do with, which I've encountered, is to do with the changes in the properties of the materials because you are mixing them together. And the particular thing that we see with this one in polymer ceramic composites is that adding the ceramic makes the polymer crystallize. And a crystalline polymer doesn't have the same properties as the amorphous polymer. I think it's really tempting, and I'm certainly guilty of this myself, to think of a polymer as a sort of sticky gloop that sticks everything together and doesn't do anything. But it does do things, and it does have an effect. And given that crystallization preferentially occurs at the surface between the ceramic particle and the polymer interface, you are actually placing a barrier in between those two particles, which is different to either of the composite materials which you might actually be considering when you think about the material properties. So we found, for example, that this is some FTIR on PVDF with added ceramics. So we're finding that we're changing the crystallization, we're getting a lot more beta phase PVDF, and it affects our properties. In this case, we're looking at crystallinity of polypropylene, which actually seems to go down as we add more barium titanate to the material, and that changes the properties again. So it's an interesting effect that we see in some of these materials. And that can also have an impact in a related sort of area, which is that we see difficulties encountered because we reach a maximum value at which we can add things. And sometimes that's due to all the additions in the material joining up together in this thing called percolation, where you form a connected network of all the particles and they're all sitting next to each other. And that changes the properties of the material. Sometimes it's just because you have all sorts of interactions between the materials, and they can't actually mix enough to be able to interact in that way. But in practice, what we find with that is that there's a really strong limit, for example, to how much ceramic powder you can put into a polymer and still make it into a printable filament or an extrudable sheet of material. And we found different values for different materials. It's not a universal law. It seems to be about 30 volume% for most things, but you can push it higher. We have pushed it higher. We've also found it come out lower, depending on what degree of mixing we've had. And it can really quite radically change the material. You know, this is some tensile tests on some 3D printer filament that we were making with the barium titanate particles inside it. You've got a stretchy, plasticky kind of structure until suddenly you don't, and you have a brittle one, which you then can't print with because it's too brittle to feed through the printer. So this can make a really quite big effect on what we see. And the final one, and I think perhaps one of my first calls for some assistance on this, one of the things we struggle with as manufacturing people is that it's very difficult for us to measure the properties of the materials we're making. The techniques that we have, we typically use a VNA, and we either do waveguide measurements or we use this coaxial line that we can place the samples in, or we do a resonant method, which is what we tend to do here. But all of them have massive sample preparation challenges. And I don't know whether this is fundamental, but yeah, it's certainly something I'd love to talk to people more about is, are there any easier ways that we could measure some of the properties of these materials to just know if we've got the right values in a reasonably simple way? Because, for example, for this technique, we have to make these little sort of a bit like a sort of polo mint or something like that with a hole down the center. And we struggled to make this in high ceramic loading with polymer. We struggled to make this because we had to drill the hole, and you can see it's not a particularly clean structure. The holes aren't always dead center. It sort of depends how it went as the drill bit went in because they're slippery. So these are quite a challenge to make in polymers. They are absolutely impossible to make with a ceramic. We cannot do it. So for the work that Abhijit's been doing over the last few years, he's had to be making these very thin sheets of ceramic material. And he probably won't thank me for showing this, but you can see some of his samples have sadly cracked during that preparation process. And that's really, it's a depressing thing to happen. It's happened to all of us as samples have broken, but it's because you get this warpage in the material. When you're trying to make it so thin, the whole surface of the material will warp during the heat treatment. When you're trying to grind it back to being perfectly flat and parallel, which is what we need to do these measurements and get the accurate values, the chance of it cracking is really quite high. So it's a very difficult thing to do. It's very difficult to measure. And I think ideally we would have more mechanisms by which we can quickly assess the properties of the materials. And I think modeling can help with this, but only if the input values are accurate. And a lot of the input values out there in the literature seem to be not particularly accurate. They're measured in strange ways and ways that when you then come to use them in a constructed device, we don't actually see the properties to the same values that we would expect. And the reasons for that are sometimes quite complicated to understand. So the second area where we've encountered difficulties, and it's not confined to mesh materials, it's a pretty universal problem, is that if you're trying to co-process materials of different properties, it makes processing very, very difficult. So if you're thinking about processing something that contains a metal component and a ceramic component, if you want to do that at scale, you probably want to process it in a minimal number of steps and preferably do everything at once. So what do you compromise on? Do you compromise on having a dense ceramic that is mechanically robust and will make you a baseline to use that metal for a long time to come? But then you have to take it up to a really high temperature to get the densification, and your metal will melt. So it's very difficult. And we have the same problem in solid state batteries. A lot of my group work on solid state batteries because obviously it's like funded area. And in that, we have the same problem where we're thinking about how do we process a solid state battery in one go and get a dense ceramic, get the properties that we need. So we do things typically in my group. We say, well, we can't do much about the metal. Let's look at the ceramic, and we look at low temperature ceramic processing techniques. A couple of examples here, flash sintering, with the furnace temperature being lower, and you pump the energy directly through the ceramic component by putting an electric current through it. Short duration, dense sample, very nice, or cold sintering, which is a really new method where you can use a different type of densification mechanism to densify at really low temperatures. So there are ways that we can start to come around some of these things, but partly the problem here is knowing about them, knowing people who can do them and knowing people who can help you with them. Another challenge with co-processing materials I struck on earlier, and it's to do with these thermally induced residual stresses. So if you make a material which contains materials which have quite different mechanical coefficients of thermal expansion, for example, you find that at the temperature you process it at, it's all fine, but when you cool it down, those differences in thermal expansion coefficient can pull the sample apart. So I had to go and raid my rather depressing folder of broken ceramic pieces from a project I did where it was basically breaking everything every time. So this is a ring of material, and this is a piece of it. And it consists of aluminium oxide at one end and silicon carbide at the other. And the difference in expansion coefficient between those two materials is pretty much double. So the material tries to pull itself apart. And I went through 6 months of basically pulling broken pieces of material out of the furnace. And then we took a bit of a step back and had a look at what's going on with the residual stress, and found that actually you can mitigate some of these residual stresses by taking this sort of graded layering approach to the material. We can gradually change those properties in this direction. And this is work I did actually before I even started on metamaterials, so it's sort of related but not the same. And we can find that we can do these modeling pieces of work and actually measure the residual stresses and find ways to keep those below the level at which the material will crack and pull itself apart. But they can do it. Avijit's samples, you know, a lot of them for a long time were breaking until he found ways to moderate that and prevent that happening during the processing. And it is very, very challenging to come around. The third challenge around co-processing materials is to do with continual change. A lot of the designs I see for metamaterials have some kind of degree of continuous change in properties, and those can be really hard for us to actually make. So we normally resort to doing discrete layers, but sort of knowing when is that going to be okay. We still want to develop continuous changes in properties, but it really isn't very easy. And the discrete layers are significantly easier to make, but these interface effects, we don't really know how much of an effect they're going to have. And the porosity effects that we get in materials often lead to reductions in their allowable effective values. So if you're doing something like 3D printing, these are some 3D printed ceramic composites, you get a lot of porosity. And unless you're going to work a lot at post-processing, which probably eliminates why you were doing the 3D printing in the first place, you need to think of these materials as actually containing quite a lot of air in that structure. And the final place where I think that I struggle, particularly when I'm thinking about metamaterials projects, and especially where we're not working really directly with a metamaterials group, is about what happens if it isn't perfect. You see this perfect design, you think, well, it's really hard to make. I don't know if I can make that. But is there any point making it if it's not going to be perfect? Sometimes you just can't make it the way it's supposed to be made. And I think as manufacturers, we don't really know what's critical for the intended application. And we don't normally have the ability to test these things as we go along. So if we're making something that's designed to be a certain type of lens or a certain type of surface, we're reliant on other people testing it. And that really means that projects have to be much, much more integrated together. So I found this paper recently, and it's partly what's inspired this part of the talk. This is a paper from Capato's group, and they were making holes again in silicon, making this meta surface. These are really quite deep holes, which is quite interesting for the aspect ratio. You can see the cross section here, they're coming down. And this is entirely what I would expect you to get, because you've got a certain degree of drift, so you get some movement while you're doing the focused iron beam work and removing the material. You get some inconsistencies in the shapes of these holes. And my question is, like, how much is that acceptable? How much of this is okay? And there's a sentence in this paper where they said most of the holes were within the acceptable range of plus or minus 16 nanometers. And that word most is doing a lot of heavy lifting in that sentence, because it's not really that well understood what that means. And what you see in this graph, where they show what it is indeed most, but some are a little larger and some are a little smaller. And my question, if I'm making this and saying, okay, well, is this good enough, is, does it matter? Does it actually matter? And in this case, they'd actually done that work and showed whether it matters. And you can see that actually the designed line and the measured line are not that far apart. There really isn't that much difference. This is probably good enough for what we need. And it's really very close together. But there is no way I would be able to do that testing in my lab. It has to be done by working together. And that's where one of the problems comes up, I think, with some of these projects, is that we sort of step through a process of design, manufacture, test, and we never circle back and are able to go through that process again. And it's often because there's not enough time. That can be a real challenge. So let me propose some solutions in the last couple of minutes, because I want to give a little bit of time for questions. One of the solutions to this is looking at materials available and hopefully moving beyond what can be bought from sort of known suppliers who will tell you this is what's on the data sheet. So that's obviously what you're going to get, which isn't actually the case in a lot of cases. And expanding those materials and having some kind of way of actually recording the properties of these materials in a centrally accessible database, which actually reflect the material properties, not just the materials chemistry, but the microstructure and the processing conditions as well. I think we need to reach out to the manufacturing community about metamaterials, and I think the network is starting to do that, and we are starting to draw people in and starting to get people interested and into those discussions with metamaterial designers, because metamaterials actually need all of the materials out there. This isn't a job for ceramics people only. It's not a job for the metal specialists only. It's a job for everybody. I think we need more synergistic collaborations between people. We need more manufacturing capability and a greater range of manufacturing techniques and materials available to people designing metamaterials. And we need to think about scale up from an early stage. So hopefully the future for UK Metamaterials is talking to each other and funding cyclical research projects, which give enough time to move around the circle of theory, design, manufacture, test, and go back again in response to testing, because I think that is the way that we need to design projects as we move into more collaborative times. And a final plea for some awareness and willingness on both sides. I think manufacturers need to be willing to compromise on some aspects of manufacturing to meet those metamaterial requirements. These are really challenging materials to make, and you have to be willing to say, well, okay, I have to accept that it's not going to be as strong as I might want it to be. I have to accept that it's not going to be done in the way I want it to be done. And for metamaterials and application specialists, I think awareness of those manufacturing limitations and awareness that there probably isn't a bespoke method out there waiting for you to find it. It needs to be worked on and it needs to be adapted to overcome some of these challenges. So at that point, I would like to thank you very much for your attention. And I'm just going to stick up a last slide to just promote some of our Metamaterials Network activities. We have the conference coming up next May. We have lots more manufacturing and scale up SIG activities for 2022. Hopefully, COVID permitting, we will be able to meet in person. So Nick Grant and Chris Tuck, pictures there at the bottom, are going to be leading the network. I'm going to be helping because I still want it to succeed and leading our SIG in doing some of these activities, and hopefully a chance to come and visit some of the manufacturing institutes and see some of our technology in practice. So thank you very much for your attention. I'm happy to take questions.
Thank you very much, Claire. That was a great talk. In particular, I'd like to thank you for summarizing the key challenges around the properties. Well, what I would now call the 3P: properties, processing, and perfection.
That's really good. Yeah, thank you, Anya.
You did indicate a couple of solutions there, and I'd just like the audience, if you'd like to ask questions, I'd like to ask the audience, if you want to ask questions, please stick your hand up. In the meantime, I will just have a quick look at the chat. I think Pete Hobson from Kinetic already indicated that they're looking at one of the problems around properties quite deeply in Kinetic. Pete, would you like to expand on that in this forum or take it offline?
Well, I'll just give probably worth a more in-depth conversation later, but just at a sort of top level, Claire was highlighting some of the issues in terms of manufacturing test pieces and rapidly testing them, and that's certainly a problem that we grapple with at Kinetic, and not just at sort of ambient temperature as well, as sort of as a function of temperature. So it's quite a complex problem, and we're sort of always keen to discuss new options for doing that, and chat about well, access to our facilities in some instances.
Yeah, fantastic. Let's talk, definitely.
I was going to also, as I've got the mic, cheekily add, I've got an interest in ceramic materials for optical applications. Is there anything you can say about that? Obviously, it's quite a challenging space to work in.
It really is. It's not something I work on at all, because it is really difficult. And I think some of the material properties you need are very challenging. But what type of optical properties would be my question?
Well, obviously transparency, just getting transparency in the first instance is challenging, because you obviously need to control so much of the microstructure and also start with high purity ingredients.
I think it's really difficult, and I know I've got ceramic colleagues on the line who will be nodding. I can see Vaidi and Sandy's here from Lucidian. A big problem, and very difficult to not end up doing some quite extreme processing to get those kind of properties in materials. But again, something that people actively work on, and I think maybe a bit more alignment between the manufacturing and the application space is what's called for there, because I think often as manufacturers, you're not going to just go and make something for the sake of it. I'm not going to get funding for it. I might be able to do it just as a fun thing on the side, but if you want to do something seriously, you have to be driven by some kind of application in the end. That's how all our funding proposals work. But if there's a really strong pull there towards something, then there's a good reason to try and develop some of these techniques and push them towards that kind of end of things. And I think that's really what's happened in solid state batteries. We've got a real market pull. There's a lot of interest. We know that the problem in a solid state battery is the ceramic electrolyte. It's the difficult bit to process. So there is then opportunity to work on it, and that's what is really needed. So yeah, very happy to talk about it, and I'm sure other colleagues will be as well.
Lovely, thank you very much. I'm going in order, so whenever questions were posed, chat first. Bala, you said you made a couple of comments actually. Do you want to expand on these comments, or is it just a takeaway for Claire for consideration?
Yeah, I mean it is. I mean, basically, just I looked at the specific requirements in terms of making complex shapes to make the measurements in the first place. Probably 3D printing could help along those lines. So a simple robocasting kind of approach could allow, and also even your polymer ceramic composites could be done through FDM type of approaches in terms of 3D printing. So shape complexity, they're not really very complex shapes for 3D printing.
They're not. I think that the challenge we've had with the FDM, so we've done some fused deposition modeling, manufacturing, and the problem we've tended to have is getting enough ceramic into the polymer to actually see any kind of functional effect at micro frequencies. I'm sure you've seen the same thing. So Vaidi is one of my few allies in being a person who works on metamaterials and manufacturing, and I definitely think that there's a work to be done there for sure. But I think with the 3D printing, part of the problem I have with it is that we do need these materials for the measurements to be really, really flat and perfectly shaped. And I have certainly a lot of uncertainty about whether, if we don't actually achieve that, do we get a real measurement? And often we see a lot of noise and we can't work out what's going on.
Sure. It depends on the technology, and again, SLA based techniques could probably give you a much better resolution on the surface quality compared to FDM maybe. But because you have the polymer, you have the advantage of probably do some post machining, if it is post polishing even.
It's just what we're trying to work on, having only ceramic. It's an all ceramic approach.
It's all ceramic. Sure.
Right, we've got a couple of questions in the chat still, and Roger's got his hand up. Maybe Roger, if you fire first.
Yes, thanks very much, Anya. I really enjoyed the talk. I thought it was a great summary of quite a difficult field, really. And particularly your last point about what matters, you know, this thing about quality, tolerancing, and the element that of course was missing, which was cost. So it seems to me that you can very often push things in that direction, tolerancing, quality, but it does take money. And behind money comes markets, you know, volumes and all those other lovely commercial things. So, and of course, these things will have to go hand in hand. So I might be able to help. You're based at Warwick Manufacturing Group?
I am, yes.
So my background is physics at Exeter, which is, of course, as we all know, an excellent university, particularly the physics department. And then a PhD with Alan Windle in Cambridge on polymers and processing and stuff. And then most of my time working at TWI on interfaces. So I was particularly interested in the interfacial aspects that you sort of hinted at. So you put two materials together and very often you've got instantly three things. So you've got the two components and then the interface or interphase, and that again can also be the source of some variation. I also wanted to make the point that very often in manufacturing, what you try and do is keep the manufacturing process constant, because it's so hard to maintain microstructure, even trying to keep things the same. So if you're trying to use microstructure control things, that's really quite challenging, I find, in general in manufacturing engineering, but why not? I mean, in certain cases, that's going to be how it is. And if we could get to that point, that would be excellent, of course.
Yeah,
so
it's pushing the limits
for various reasons. So maybe if I could drop in and have a chat sometime, that might be helpful. One final thing from me. I did work on antennas for a couple of years, and we had these things called dielectric resonating antennas, which was essentially a lump of ceramic which was excited. And it might just be, if you can keep the geometry pretty much the same and change the process, you might be able to measure the properties of that particular type of antenna and then infer back some of the dielectric properties that you've got in the material. It's just a thought. So it would be some sort of bounded system, and with a VNA you might be able to make some sort of I think there's probably some papers out there talking around the properties of DRAs, and there would be a dielectric part in that. So it may be that could be a way of helping you out on the dielectric side. Anyway, I'll drop in sometime if that's okay.
Yeah, that'd be great. Drop me an email, and yeah, definitely. Once we're allowed to go and see people.
Yeah, thanks again. Great talk.
Thank you.
Lovely. So on that note, we actually reached the end of our session today. We've got a couple more questions in the chat. Claire, I would probably post them in writing over to you, and maybe we can disseminate the slides among the participants. Would that be all right? Together with the responses, the written responses to the questions. Lovely.
Absolutely.
Okay. Well then, thanks again for a very interesting talk. We would have loved to host you here. Hopefully next year we'll, bring you down to Exeter in person. Thanks to the audience for joining in. And if you have any further questions or would like to get in touch with Claire, please do let us know. Happy to facilitate the link, or you can obviously find her details on the web as well.
Yeah, please do. Thank you.
Bye everyone. Have a lovely Christmas when you get there.
Thank you.